SwayamPrabha. Digital India. Educated India.
Good morning. Today I'll solve some problem on reaction turbine. An electricity generating installation uses a Francis turbine with a rotational speed of 1260 rpm. The net head across the turbine is 124 meter and the volume flow rate is 0.5 meter cube per second. The radius of the runner is 0.6 meter and the height of the runner wing at inlet is 0.03 meter and the angle of the inlet guide vane is set to 18 degree with respect to the tangential direction, assuming that the absolute flow velocity is radial at exit. Find the torque and power output. Calculate also the hydraulic efficiency. Let me solve the problem. Quantities given are: N is the rotational speed of the impeller is 1260 rpm. Head given H is equal to 124 meter. Flow rate Q is equal to 0.5 meter cube per second. R1 radius at inlet to the rotor 0.6 meter. Height of the blade at inlet B1 0.03 meter. Alpha 1 is given as 18 degree with respect to tangential direction. Alpha 2, there is no swirling component exit, so alpha 2 would be equal to 90 degree. These are the quantities given for a Francis impeller. We'll have to evaluate torque, power developed, and hydraulic efficiency eta H. Let me first draw the velocity triangle. This is the meridional view of the blade. So this is U be the tangential velocity. So at inlet, W1 be the relative velocity. And W2 be the exit velocity, relative velocity. Thus, U plus W1 would be equal to C1. So this is the velocity triangle at inlet to the impeller, and this is alpha 1 absolute inlet angle, and this is beta 1. Thus at exit U, W2 plus U would be equal to C2. C2 is nothing but Cm2, and this alpha 2 would be equal to 90 degree. There is no swirl at exit. This angle is beta 2. So I have drawn the velocity triangle for a Francis turbine. Thus I can write torque developed, torque on the impeller is equal to m dot r1 c theta 1 minus r2 c theta 2. Now c theta 2 is equal to 0, so this part would be equal to 0. So torque would be equal to m dot r1 c theta 1. Now m dot can be written as rho into q to r1 in c theta 1. This is the expression for torque. So rho is equal to 10 to the power q. Q is given as 0.5, R1 0.6 multiplied by c theta 1. If you do the calculation, it would be 300 into c theta 1. That is the expression for torque. Let me put this as equation number 1. Now, inlet area that's flow area at inlet. If it is A, that would be equal to twice pi R1 into B1. So let me put the values. Thus A would be equal to 2 pi into 0.6 into B1 is 0.03. If you do the calculation, it would be 0.113 meters squared. Now Cm1, meridional velocity at inlet. Now let's refer the inlet velocity triangle. So this is Cm1. This is c theta 1. This length. This length is w theta 1. The Cm1 we can get Q by A. So we know the value of Q as 0.5. A I have calculated 113. That would be equal to 4. From this one can project c theta 1 is equal to Cm1 divided by tan alpha 1. This is equation number 2. Thus from equation 2, we can write C theta 1 is equal to Cm1 divided by tan alpha 1, that is 4.42 divided by tan 18 degree. If you do the calculation, C theta 1 would be 13.6 meter per second. Now from equation work, I can express torque as 300 C theta 1, that is equal to 300 into 13.6 equal to 4080 Newton meter. Thus I got one answer, that is torque is equal to 4080 Newton meter. Now power P can be written as T into omega, that is equal to torque into 2 pi n divided by 60. Let me put all the value now. 4080 into 2 pi, what is the RPM? 1260 divided by 60. So if you do the calculation, it would be 538 kilowatt. Thus, we have got power as 538 kilowatt. This is the another answer. Therefore, eta H, which is hydraulic efficiency, will be expressed as power developed divided by available power. Now power developed is this P that I have evaluated, and the available power, that is the power of order, that would be rho Q G into H. H is the effective head. Just let me put all the values. This should be equal to 538. This is the kilowatt, so multiplied by 10 to the 3 divided by rho 10 to the power 3, Q into Q would be equal to 0.5, G 9.81 into head is 124. If you do the calculation, this would be 0.885. Thus I have got another answer, which is hydraulic efficiency, that I've evaluated as 88.5%. Thus, I've solved the problem. I'll solve here another problem on Francis turbine. The statement of the problem is a Francis turbine has a diameter of 1.4 meter and rotates at 430 rpm. Water enters the runner without shock with a flow velocity of 9.5 meter per second and leaves the runner without swell with an absolute velocity of 7 meter per second. The difference between the sum of the static and potential head at entrance to the runner and at exit from the runner is 62 meter. The turbine developed 12.25 megawatt power and has a flow rate of 12 meter cube per second of water when the net head is 115 meter. Find the absolute velocity of water at the entry of the runner and the angle of inlet guide vane. Second, the entry angle of the runner. And the third, the head lost in the runner. I'll solve the problem now. The quantities given: D1, diameter at inlet to the runner is 1.4 meter. RPM, rotational speed of the runner N, is 430. Meridional speed at inlet CM1 is equal to 9.5 meter per second. C2 would be equal to meridional speed at exit because there is no swelling component. So you can write CM2 is equal to C2 exit absolute velocity, that would be equal to given as 7 meter per second, since C theta 2 swollen component and exit is 0. Furthermore, del H head difference static, S for static, plus del Z difference in elevation between inlet and exit is 62 meter. Power developed by the turbine P is 12.25 megawatt. Flow rate Q is given as 12 meter cube per second. We'll have to evaluate C1, alpha 1, beta 1. And loss in the learner, that is loss in the learner, I can say HR. HR stands for loss in the runner. Hence, let me first draw the velocity triangle in a Francis turbine. So this is the blade. Let's consider the blade speed is U. Thus, W1 be the inlet relative velocity and W2 with the exit relative velocity. Therefore, at inlet, U plus W1 results in C1. C1 makes an angle alpha 1 with respect to tangential direction. Now this angle is beta 1. If we project C1 in the meridional plane, this will be CM1. CM1 is given as 9.5 meter per second, and projection of C1 in the tangential direction is C theta 1. Similarly, at exit, if we draw the velocity triangle, U plus W2 would give C2. Swallowing component at exit is 0, so C2 must be equal to CM2. Alpha 2 would be equal to 90 degree, and this angle is beta 2. Thus, I have drawn the velocity triangle both at inlet and exit in a meridional plane. Thus, let me solve the problem now. So U, blade speed, I can write at inlet pi T1 in divided by 60. Now, let me put the value. T1 is 1.4, N is equal to 430 divided by 60. If you evaluate, it would be 31.52 meter per second. Now I can say power developed P is equal to m dot u1 c theta 1 minus u2 c theta 2 for a turbine. But here c theta 2 is equal to 0, so it will be m dot u1 into c theta 1. So I can write rho q u1 into c theta 1. Now u1 I have evaluated 31.52, and P expression for P is given. So what is P? P is 12.25 megawatt. So 12.25 10 to the power 6 is equal to density is 10 to the power 3. Value of Q is given as 12. U1 I have evaluated as 31.52 into c theta 1. So I can evaluate the value of c theta 1, and after calculation I got c theta 1 as 32.45 meter per second. Thus, from inlet velocity triangle, I can write tan alpha 1 is equal to Cm1 divided by C theta 1. Cm1 M1 value is given as 9.5 meter per second. C theta 1 I have evaluated as 32.45. Thus, after calculation, I got alpha 1 as 16.317 degree. So this is the one answer. So I have evaluated alpha 1. Now C1 is equal to root over C theta 1 square plus Cm1 square from inlet velocity triangle. That would be equal to root over C theta 1 has been calculated as 32.45 square plus Cm1 is given as 9.5. If you do the calculation, you will get C1 as 33.81. Please check all the calculations. So I got another answer, which is C1 as 33.81 meter per second. Now I'll go to the next section B. Now again from inlet velocity triangle, I can write 180 degree minus beta 1 is equal to tan inverse Cm1 by W theta 1. Now Cm1 W theta 1, I can write C theta 1 minus U. Let me put the value. Tan inverse Cm1 is equal to 9.5. C theta 1 I have calculated as 32.45. And U is equal to 31.52. If you evaluate, you will get this is 84.77 degree. Thus you will get beta 1 referring to the velocity triangle equal to 95.23 degree. So I have evaluated beta 1. Now let me go to the third part, C, where H1 equal to head at inlet P1 by rho G, static head plus dynamic heads C1 square by 2G plus jet elevation. Similarly, H2 would be equal to P2 by rho G plus C2 square divided by 2G plus Z2. This should be Z1. So I have put the expression of H1 and H2. That is head at inlet, total head at inlet, and total head at exit. Thus, let me go to the next. Hence, H1 minus H2 can be stated as del H across the turbine is equal to P1 minus P2 divided by rho G plus C1 square minus C2 square divided by twice G plus Z1 minus Z2. This can be stated as difference in static aid between the inlet and exit of the turbine and can be designated as del H S, or this is as del Z, the difference in elevation. Hence, we can write del H head across the turbine is equal to del H S plus del Z plus C1 square minus C2 square divided by 2G. Let me put the value. Del HS plus Z is given as 62. Now we know the value of C1. C1 is 33.81. C2 is given as 7 divided by 2 into 9.81. Now if we evaluate, we'll get del H as 117.765 meter. Now, work output per unit weight can be given by small w is equal to U1 C theta 1 divided by G, since C theta 2 is equal to 0 here. Thus, loss in the runner, I have designated loss as HR is equal to this del H head difference minus, which is the work output, that is U1 C theta 1 by G. Now let me put the values, that 117.765, which I have evaluated here, minus U1 is 31.52 into C theta 1 as 32.45 divided by 9.81. If you do all the calculation, you will get 13.5 meter. Thus, I got another answer, which is the head loss within the runner is 13.5 meter. This is the third answer. And with this, I have solved the problem. Now I'll solve a problem on Kaplan turbine. The statement of the problem is a Kaplan turbine designed with a power specific speed of 3.0 radian, a runner tip diameter of 4.4 meter, a hub diameter of 2 meter, operates with a net head of 20 meter and a shaft speed of 150 revolution per minute. The absolute flow at the runner exit is axial. Assume that the hydraulic efficiency is 90%. Determine the power output and the volume flow rate. The relative flow angle at the inlet and exit with respect to the tangential direction of the runner mean radius. I'll solve the problem now. The quantity given are head is equal to 20 meter, dimensionless specific speed omega sp is equal to 3.0 radian, rpm rotational speed of the impeller is 150 rpm. Tip diameter dt is given as 4.4 meter. Hub diameter dh is 2 meter. Kaplan turbine is an axial flow machines. So we'll have to evaluate P power output, Q flow rate through the turbine, beta 1 and beta 2 relative flow angle. Let me draw first the velocity triangle of a Kaplan turbine. So I have drawn the blade profile. It's an aerofoil constructions. This is U is the blade speed. Let me consider W1 be the inlet velocity, inlet relative velocity, and W2 be the exit relative velocity. So at inlet, U1 plus W1 results in C1. And this angle is beta 1 and this is alpha 1. This is tangential direction theta and this is axial direction z. At exit, W2 plus U2 would be equal to C2. Here C2 are in the axial direction and this is alpha 2. Alpha 2 would be 90 degree here and this is beta 2. So I have drawn the velocity triangle for a cup 1 turbine blade both at inlet and exit. And here U1 must be equal to U2, that's say U, that is equal to blade speed. So I can write here U1 is equal to U2, this is U say. Now from the given data, I can calculate omega, rotational speed in radian per second, that is equal to 2 pi n divided by 60. We know the n is equal to 150 rpm. Put the values of n here. You will get 15.71 radian per second. Now we know power specific speed, omega sp. The expression is omega root over P by rho divided by GH to the power 5 by 4. Power specific speed is given as 3. Put the values. Omega I have evaluated as 15.71. Root over P density is 10 to the 3,000. G 9.81. What is the value of H? H is equal to 20 meter to the power 5 by 4. From here one can evaluate P. I have got P as 19.66 megawatt. This is the power. Please check the calculation. Now hydraulic efficiency eta H, expression for eta H is equal to P divided by rho G Q into H. Now we know the value of power, and furthermore the hydraulic efficiency is given here as 0.9. So another that I have forgotten to write, that hydraulic efficiency eta is equal to 0.9. So put the value, all the value here. So 0.9 is equal to P here 19.66 into 10 to the power 6 divided by 10 to the power 3 rho into G means 9.81. Q you do not know, head given as 20 meter. Thus one can evaluate from here the value of Q. If you evaluate the value of the Q, you will get Q as 111.35 meter cube per second. Thus I have got the value of Q. So I have evaluated the value of P and the value of Q then. Now tip diameter dt is given as 4.4 meter. Hub diameter dh is 2.0 meter. Thus one can evaluate from here mean diameter dm is equal to dt plus dh divided by 2. If you do this, you will get 3.2 meter. Hence, one can evaluate um, that is blade speed at the mean diameter, is equal to pi into dm n divided by 60. Let me put all the value. Pi 3.2 into n is 150 divided by 60. If you do all the calculation, you will get um as 25.133 meter per second. Furthermore, I can calculate annulus area A as pi by 4 into dt whole square minus dh square, that is pi by 4 into 4.4 whole square minus 2 square. If you evaluate, you will get 12.0637 meter square. Now, axial velocity, if Cz, that is Cz into A, annulus area would be equal to Q. Thus from here, I can calculate Cz as Q by A, that would be 9.23 meter per second. Now, head developed would be equal to U1 C theta 1 for a turbine minus U2 C theta 2 divided by D. And if eta H be the hydraulic efficiency, this is the actual head developed would be eta H. So this is the expression of actual head developed. Now here U2 C theta 2 would be equal to 0 because being C theta 1 is 0 here. Thus this should be equal to U1 C theta 1 divided by eta H into G, which is the actual head developed. Here actually actual head dropped. In case of turbine, the head drop, the pressure drop occur. So this is the actual head drop. Now from this expression one can write C theta 1 as eta H G into H. Value of H is given as 20 meter divided by U1. Now let me put all the value. eta H as 0.9, G is 9.81, head as 20, and U1 evaluated as 25.1 cc. Now this becomes 7.026 meter per second. Thus, I have calculated C theta 1 here. Now from inlet velocity triangle, I can write tan beta 1 is equal to Cz divided by W theta 1. W theta 1 I can write as U1 minus C theta 1. Cz has been evaluated as 9.23 meter per second and U1 is 25.1 cc minus C theta 1 as 7.026. If you do the calculation, it would be 0.5097. Thus, beta 1 would be equal to 27.01 degree. Thus, beta 1 has been evaluated. Now, I'll have to calculate beta 2. Now, similarly, beta 2 can be given by tan inverse Cz divided by U2. Here U2 would be equal to W theta 2. Put the value tan inverse Cz equal to 9.23 divided by U2 is here 25.1 cc. U2 is would be equal to U1. So if you do the calculation, beta 2 would be equal to 20.166 degree. Thus, I've got beta 1 as 27.01 degree and beta 2 as 20.166 degree. So I have solved this problem. I have solved 3 problems here, 2 on Francis turbine and 1 on coupler turbine. Hope it would be helpful to you. Thank you for listening.